Let's do an example here now where we have a circuit with capacitors and resistors attached to a source of potential. It has a switch and an ammeter. We're trying to figure out what does the ammeter read as soon as we close the switch and what does it read after the switch has been closed for a long time. So let's tackle part A first. What happens as soon as we close the switch? Well, what happens that as soon as we close the switch, so just after the switch is closed, we know that we get a maximum current flow through our capacitors. It's easy for current to flow through the capacitors. That means a capacitor is like a short circuit as soon as the switch is closed. So if it's like a short circuit, it's just like a piece of wire. So let's think about what that means in terms of our circuit. I've quickly resketched my circuit here. If we replace our capacitors with pieces of wire, will any current flow through resistors that are in parallel with the capacitor? Definitely not, because when a current flows, if it has a choice between going through a resistor or going through a piece of wire, it's definitely going through the piece of wire. So all charge will go through a capacitor and none through a resistor in parallel. Let's look at what that means for our diagram. So our current leaves our battery, comes up, hits a branch. When it comes to this branch, it is not going to flow through that top resistor because that's hard to do. It's going to flow through the capacitor. And it's going to hit this resistor. It has no choice. Then it comes to a junction. Part of the current is going to flow this way. When it gets to this junction, it has a choice. It can go through the capacitor. Remember, that's like a piece of wire. Or it could go through the resistor. It's not going to choose the resistor because that has a resistance to current flow. So it will come down through this branch, down through here, back around. Part of the current will also flow down through this branch, then it'll recombine at this junction and come back through the ammeter. So that's what our current is going to look like. Let's redraw our circuit, getting rid of all those all the resistors in parallel. So we've got the battery, we've got the first capacitor with the resistor, comes down, next capacitor, a resistor, down, a resistor, an ammeter, back around. Okay, next branch over, I've got that. So let's see if I can just get it nice and clear here. So this becomes like a single branch, so I'll just put that in a branch up here. Got a capacitor and a resistor. Okay, so this is what the circuit looks like a bit simplified. But if our capacitors are short circuits, they act like pieces of wire. So let's replace capacitors with pieces of wire. That's because our capacitor acts like a short circuit. It's very easy for the current to flow through it. So our first capacitor is a piece of wire. I've got a resistor. Next capacitor is a piece of wire. At the bottom, I've got my ammeter and my resistor. Then my far right branch, the capacitor is a piece of wire, and I've got the resistor. I'm going to label in my resistances here now. So I've got a 15 ohm resistor on the bottom. I've got a 75 ohm resistor on the top. And I've got a 50 ohm resistor in the middle. And I've got a 25 ohm resistor on the outside. Our question is asking, what is the current flowing through the ammeter? So that would be the current that comes out of the battery or the current that goes back in. Okay, this is a problem we've dealt with before. This is really just finding an equivalent resistance and calculating the current that flows through it. We can either do Kirchhoff's laws or we can do equivalent resistances. I think I'll do equivalent resistances just because we haven't practiced that in a while. For this branch, those two resistors are connected in parallel. When you have resistors in parallel, to get the equivalent resistance, you know that 1 over R equivalent is 1 over the first resistor, 1 over 50, plus 1 over the second resistor, that would be 25. That's equal to 3 over 50. I'm a fractions person, so I did fractions. If you were a numbers person, you'd probably just have that as the number right off the bat. So this equivalent resistance is 50 ohms over 3. I'm going to leave it as a fraction, but again, you don't have to if you prefer not to. We'll draw a new circuit that's got our battery, got our resistance, it's got that new equivalent resistance, got the lower resistance. So that's 75 ohms. This is 50 over 3 ohms. And this one is 15 ohms. All of these resistors are in series. And to find the equivalent resistance when you have a set of resistors in series, you just straight up add them. So 75 ohms plus 50 over 3 ohms plus 15 ohms. Let's go for numbers this time, 106.7 ohms. Let's draw our last equivalent circuit where we've got our battery that has a potential of 100 volts. It's got one last equivalent resistance. Dropped my ammeter in the previous step. I'll put it back in here. I'll try and fudge and put it in over here too. My current is leaving the circuit and going around, so there's my current I going around the circuit. My new equivalent resistance is 106.7 ohms. I can apply Ohm's law, which says that V equals IR, so my current is going to be my potential divided by my resistance, 100 volts, over 106.7 ohms, 0.938 amps. So that's the current output by the battery as soon as we close the switch. For part B, we want to find the current after that switch has been closed by a long time. Let's work on part B now. What is the reading of the ammeter after the switch has been closed for a very long time? So what does it mean if the switch has been closed for a very long time? After a long time, the capacitor is fully charged. Every capacitor is fully charged. What does it mean if a capacitor is fully charged? Well, it means no more current can flow. The capacitor that's fully charged, any capacitor that's fully charged, has as much charge as it's going to get on its plate, and no more charges can move around. That means a fully charged capacitor acts like an open circuit. So, in our circuit diagram then, our 15 microfarad capacitor is now an open circuit. No current goes through that branch. The 20 is an open circuit. No current goes through that branch. And the 10 is an open circuit. No current goes through that branch. Let's look at where the current can flow. It comes out of the battery, comes here, it hits a junction where it can either go through the open circuit, which it can't go through, so it's forced up through the 25 ohm resistor. Comes down, goes through the 75, comes to a junction. It can't go down because that's an open piece of wire. Then it comes to a next junction. It can either go down or it can go right. Can't go to the right because that's an open circuit, so it has to go down. So it comes down through here, goes left, can either go up or continue on left. Can't go up because there's an open circuit. Current can't flow through that branch and goes through here. So this is our current flow after the switch has been closed for a long time. Let's draw a new circuit diagram. So we've got our battery, comes up, we've got a 25 ohm resistor, got a 75 ohm resistor next, then we come down and we've got two 25s, then we head to the left, we've got a 15, and we've got an ammeter. So this is what our new circuit diagram looks like. I'm going to label in all of those resistors. 25, 75, 25, 25, and 15. This one is a real simple circuit to analyze. All of those resistors are in series. So the equivalent resistance is 25 plus 75 plus 25 plus 25 plus 15 equals 165 ohms. So we can draw a new circuit diagram where I've got our battery, the equivalent resistance, the ammeter, I almost forgot it again, and then we have current coming out of our battery. We're going to try and find our current. We'll just use Ohm's law. Ohm's law says V equals IR, so the current is equal to the potential divided by the resistance. 100 volts over 165 ohms to get 0.606 amps. So the current drops after the switch has been closed for a really long time. In this example, we have a 50 microfarad capacitor which has been charged up to 3000 volts and it's discharged through a resistor. The figure shows the capacitor voltage as a function of time. We want to find the value of the resistance. So this is a simple RC circuit. We're going to try and find the resistance. Let's start by recognizing that we'd like to write down the equation for potential. To find the equation for potential, let's write down what we know about the current in the circuit as a function of time. I is equal to some maximum current, I.O., times e to the minus t over tau. T is the time, tau is the time constant of the circuit, equals R times C. Let's multiply both sides of our equation by R. And then recognize that from Ohm's law, V equals IR. So the change in potential, or the potential across the capacitor, is the initial potential across the capacitor times e to the minus t over tau. This equation is pretty good because we can read some stuff off the graph. So from the graph, at t equals 2 milliseconds, or let's start with 0. If t is equal to 0, our potential, delta V, is equal to 3000 volts. So that's our V0. And if, let's pick another point on the graph, at 2 milliseconds, that's kind of easy to read. At t equals 2 milliseconds, that means 2 times 10 to the minus 3 seconds, our potential at that point is 1000 volts. Now we have some things we can put in the equation. So let's start filling some stuff in. So delta V is 1000 volts. That's equal to our initial potential of 3000 volts times e to the minus t, that's our time, that's our 2 milliseconds. I'm going to work in milliseconds here, and I'll just keep in mind that that's going to give me my tau in milliseconds. If you don't like that idea, then you can right off the bat, you can write down times 10 to the minus 3 seconds. Okay, I'll divide both sides by 3000 because I'm trying to solve for tau. So 1000 volts over 3000 volts equals e to the minus 2 milliseconds. You could drop your units here. I'm going to keep them in just so I don't forget what I'm doing. If we want to get rid of our e, we have to take the natural log of both sides. So the natural log of 1000 volts over 3000 volts is the same as the natural log of 1 over 3, equals minus 2 milliseconds over tau. So tau then is equal to minus 2 milliseconds. Look at me, I was thinking about velocity and I wrote meters per second, milliseconds, divided by the natural log of 1 over 3. Do that in your calculator, you should get 1.82 milliseconds. We remember that tau is our time constant. That's R times C, so maybe it would be a good idea to convert that to seconds after all. So 1.82 times 10 to the minus 3 seconds. So R times C equals 1.82 times 10 to the minus 3 seconds. We know our C, so to find our R, it's equal to 1.82 times 10 to the minus 3 seconds divided by our capacitance C, which is 50 times 10 to the minus 6 farads. Put that through the calculator, we get 24.3 ohms. So that graph actually gives us quite a bit of information. In this example, the switch in my circuit has been closed for a very long time. Before we even get started, let's make sure we remember what that's telling us. If the switch has been closed for a very long time, the capacitor in my circuit is fully charged. If the capacitor is fully charged, and that means that there's no current flowing through this branch, and it acts as an open circuit. All right, part A now asks us to find the charge on the capacitor. Let's remember that capacitance C is charge divided by potential. I know the capacitance is 2 microfarads. If I could find the potential, then I'd be able to calculate the charge. If I want to find the potential, why don't I do Kirchhoff's loop rules for my 2 loops and see if I can find the potential. Okay, my first loop I'll take in the left-hand part of the circuit. So I'll take my loop around clockwise. I'll write my loop rule. I've got my potential due to my battery, that's 100 volts. I've got a drop across my 60 ohm resistor. So let's get my current labeled. I've got current I comes out of our battery. So minus I times 60 ohms. My current and my loop go in the same direction, so it's a drop. Then I get to my 40 ohm resistor. Let's see if we can figure out what current goes through that one. Well, normally we would get to the junction at the top. Some would go to the right and some would go down. But to the right, we have a branch with an open circuit because our capacitor is fully charged. So there's no current in that branch. So all of the current I goes down through the 40 ohm resistor. So I've got minus I times 40 ohms. That's going to give us 0. Can use that to solve and find that my I equals 1 amp. Okay, there's my first loop. That tells me the current being output by the battery. I'll draw my second loop now in the right-hand branch of the circuit. And I'll write down my loop rule for that part. Let's start with the 40 ohm resistor. I see that my loop goes up, my current comes down. That tells me I have a potential increase across that battery, across that resistor. So that's equal to the current I times the resistance of 40 ohms, remembering that my current I is 1 amp. I get to the 10 ohm resistor. Remember, I've said in this branch there's no current. So my current through my 10 ohm resistor is 0. So to find my potential drop across that resistor, I've got 0 times 10 ohms. I suppose technically you don't have to put it in at all, but it's nice just to illustrate. And then the last thing I have is my potential drop across my capacitor. That has to equal 0. So my potential drop across my capacitor is my 1 amp times my 40 ohms equals 40 volts. Okay, now I'm all set to find my charge on my capacitor. So for part A, Q is equal to C times V, and this is the potential after the switch has been closed for a really long time. So I've got 2 microfarads, that's 2 times 10 to the minus 6 farads, times my potential of 40 volts. And that gives me a net charge of 8 times 10 to the minus 5 coulombs. Okay, the next part says we open the switch at t equals 0 seconds. At what time has the charge of the capacitor decreased to 10% of its initial value? So it's almost fully discharged, but not quite. So let's see if we can figure out that time next. For part B now, the switch is opened at t equals 0 seconds. Let's just stop and think for a moment about what that means. If our switch is open, then there's no current in this branch. Because we have an open circuit. So the current that's going to flow will happen because the capacitor has been charged up. So charge is going to leave that capacitor and flow around that little circuit. So the circuit we're going to have is going to be the 40 ohm resistor, the 2 microfarad capacitor, and the 10 ohm resistor. So this is what's happening in our circuit. And we might remember that there's 40 volts across that capacitor. All right, so now let's get into the question. At what time has the charge on the capacitor decreased to 10% of its original value? Let's start with the equation for charge on a discharging capacitor. Q equals Q0 e to the minus t over tau. Tau is our time constant equal to R times C. That's where our new circuit is going to be important. Okay, so our new charge is 10% of the original charge, so it's 0.10 times QO, where QO stands for the original charge that we found in part A. You could put in numbers here if you wish. I'm more of a symbols person, so I'm going to stick with symbols. I've got my QO can cancel on both sides. I'd like to get rid of my E, so I'll take the natural log of both sides. Natural log of 0.10 equals minus t over tau. So then I'm asking for how long, what time, so my time t is going to be minus tau times the natural log of 0.10. At this point I have to find my tau, so tau is R times C. C is okay, it's 2 microfarads. What is R? So R would be the equivalent resistance of our new little circuit we drew here. These two guys are connected in series. So the equivalent resistance is 50 ohms, 40 plus 10. I won't write that out. So then our new circuit is a 2 microfarad resistor connected to a 2 microfarad capacitor connected to a 50 ohm resistor. So that's our R. R equals 50 ohms. So T equals minus RC times natural log of 0.10 equals minus 50 ohms times 2 microfarads, so 2 times 10 to the minus 6 farads, times the natural log of 0.10. Put all that through the calculator, you should get 2.30 times 10 to the minus 4 seconds. So that's how long it takes to decrease by 90%.